Good morning. We are Gator Space Innovation. I'm Michael Gottlieb.
I'm Calvin Hogg.
I'm Cooper Holcomb.
I'm Frida Dorsami.
I'm Joshua Bays.
I'm JT Russell. Halen Rampazard.
I'm Caitlin Campbell.
I'm Tom Van.
And I'm Kyle Browning.
And today we're going to be covering a technology that covers mitigating lunar dust on the Starship HLS landing gear.
We chose the SpaceX HLS instead of the Blue Origin, and with the SpaceX, it comes with the rocket engines of total of 6, 3 Raptor engines and 3 RVAC engines. Each Raptor engines has about 2.3 meganewtons of thrust, while the RVAC engines have about 2.58 meganewtons of thrust, where the RVAC is going to be used in the vacuum of space, while the Raptor is used inside atmosphere. On the top right, we have our CFD of the rocket burn, just showing the single cone, which is going to be simulating in the vacuum of space situation. On the bottom right image is the schematics of which we found online. It's maybe a little questionable if it's exactly true or not, of the Raptor and our Raptor vac engines. But yeah, these are just the rocket engines that are going to be used for the Starship HLS.
And I'll be discussing the challenges of lunar dust. And the lunar surface is a unique material, contains a unique material, which is lunar dust, and it's fine, abrasive, and electrostatically charged. It is less than 20 microns in diameter and makes up nearly 20% of the lunar surface. This dust comprises of about 80% of granitic glass with high traces of nanophase metallic iron, which is a key component in its abrasive nature. And due to its sharp edges and electrostatic charge, lunar dust poses a significant challenge. It clings to surfaces, reduces visibility, compromises vehicle systems, and even impacts astronaut health. And reports from Apollo missions and incidents like China's U-21 rover highlights the pervasive nature of lunar dust. And the health risks associated with lunar dust as well are alarming. And brief encounters can cause eye and throat irritation, and long-term exposure can lead to chronic health issues. And considering Artemis's goal of establishing a prolonged human presence on the moon, preventing exposure to lunar dust becomes crucial due to its potential hazards.
So our main objective for this project was designing a device that can mitigate the dispersal of lunar dust during descent and ascent of the HLS caused by the rocket plume. So our design process for this, we started with each of our 10 team members researching and coming up with just a basic idea of a device that we could use. And then after using a decision matrix to weigh the benefits and limitations of each of those designs, we narrowed it down to the following 3 concepts.
Alrighty, so for this, we'll go into each concept and discuss the basic design parameters of each and how they differ from each other and what eventually led us to our final design concept. So in the first concept, concept 1, it was designed to be a deployable electrostatic umbrella shield. This would be attached at the bottom of the HLS and act as a subsystem to the entire body. As you can see, it would only be deployed during the final descent to the lunar surface, and that would be when the mid body thrusters are enacted to prevent the shield from being disrupted from the Raptor engine, the excess heat from the Raptor engine. Along with that, the dust shield would be made of a flexible but sturdy-like fabric, and that would be attached to each frame of the umbrella-like shield. And that fabric would also have some type of capacitor strips to repel any type of small electrostatic charged particles. With this one, the main concern was finding out what capacitors could be used to power, what type of power source could be used to power these capacitor strips, and how that would be attached to the HLS given the frame and body makeup of the rocket itself. So we took that into account as we went further throughout our other concepts. Following that, concept 2 also dealt with some form of electrostatic manipulation. In this, though, it was 3 devices attached to the HLS legs in which they were positioned and angled at an appropriate distance so that laser beams would shoot at various spots of the HLS to protect the landing gear and any other infrastructure inside from being disrupted from the plume effects of the moon's surface. In that, using the lunar dust electrostatic charge, each device will remove a significant amount of the HLS's, a significant amount of lunar regolith on the HLS structural surface. And this also was intended to have some type of sensors that could be able to track the amount that was regolith that was accumulated and removed. With this, the main issue was finding out if the laser beams would be enough to remove a significant amount, and we answered that further in our final design. And the last concept that came up was the surface application of aerosol. This aimed to alter mainly the lunar surface as a whole to limit the regolith that was there before the HLS landed. And so with this goal of increasing the cohesiveness between the finer dust particles and that of the larger particles, the goal was to use nozzle-like instruments to mist a liquid nitrogen almost in a water form to disperse the amount of regolith on the lunar surface. The main problem with this was whether this would instead create clumps of lunar regolith instead of dispersing it. So we took that into account as we went into our final design and made all the changes necessary to find a merger that encompassed most of the applications used in these 3 concepts.
So after analyzing and discussing 3 different concepts and also applying further research, we turned into electrodynamic dust shield, EDS for short. And it's a technology developed by NASA, and unlike traditional dust removal methods such as brushes or coatings, EDS offers flexibility and eliminates concerns regarding safety and material degradation due to lunar dust. At its core, EDS employs multiple electrodes to create a non-uniform electric field with varying high voltages. When activated, this electric field interacts with the electrostatic charge dust particles and exerting a force that repels them away from the surface. Research and practical applications have showcased EDS's remarkable effectiveness, and its effects can be utilized in various scenarios. For instance, like safeguarding thermal radiators, spacesuit fabric, and also preventing camera lenses and solar panels to be damaged by lunar regolith. Our focus has been mainly on adapting EDS onto the Artemis program. And then mainly the 3-dimensional version of EDS is particularly beneficial for our application. And it's because it creates electric fields in multiple different directions and orientations. And to address the lunar dust accumulation on the Starship HLS, we're integrating EDS technology within the specific surfaces of the HLS, and the strategic application aims to mitigate dust accumulation within critical regions of the Starship HLS. And mainly we're doing that by integrating them to the landing legs of the Starship HLS.
Our final design. The EDS utilizes a 3-phase voltage system for surface electric field creations. The dimensions and components for the box are listed on the screen. Wires link the component box to the electrical source, which are sustained by the solar panel system and the electrodes. Electrodes then establish connection with the object's surface, enabling voltage application for dust repulsion. Then solar arrays and battery systems from the HLS feed through 2 powering systems in order to convert voltage for various uses, control the MOSFET, and power EDS system via electrode attachment. The finalized 3D CAD model of the EDS attached to the HLS landing gear is presented on the slide. The significance of placing the device on the landing gear demonstrates how the EDS not only plays a crucial role in ensuring that dust does not infiltrate, but also compromise its performance. The EDS offers flexibility in its placement, allowing for various orientations. By highlighting this, it shows how its functionality not only demonstrates its compatibility with diverse HLS equipment setups.
Yes, since our mitigation system focuses on the landing gear, we need proper attitude and altitude determination for preventing any damage and subsequent failure of our system and the likes. And some of the GNC subsystems included in the Orion module we found were the inertial measurement units, star trackers, and OpNav cameras. And going into more detail, the inertial measurement units communicate rotation rate and acceleration to the flight software using 3 gyroscopes and accelerometers. And star trackers determine attitude for overall operation by comparing pictures of stars to stored catalogs on board. And the OpNav cameras compare the sizes of images of Earth and Moon and provide range and bearing to the objects. And some other relevant technology found on the NASA chat websites was LiDAR, which helps positional accuracy, which could in turn help for the landing phase and proper deployment of the legs.
So to power the EDS system, we want to use the primary power sources of the solar panels and batteries that are already installed on the HLS. The use of 2 separate DC-DC converters, which can be seen in the schematic on the right, show that we are going to either step up or step down this voltage to power the different circuitry components. On the right side of this schematic, we have a cascaded step-up converter that is designed to power the MOSFET, which is going to act as a transistor that controls the alternating voltage output to the EDS. This alternating voltage output is what creates the electrodynamic field that allows the dust particles to repel one another. On the opposite side of the flow diagram, we have a step-down converter that controls the logic circuit. The power requirements of the EDS are from 1 to 36 milliwatts. This is based on the alternating voltage and current requirements of the EDS system. For the load profile of the EDS during the period of operation, which is descent and ascent, there is an alternating sinusoid with an amplitude of 18.5 milliwatts. This is necessary to avoid surging or failure of circuitry components.
Okay, so for the material selection of our EDS, we had 5 main components, including the external structure. Our first one was our series DC-DC converter, which is space qualified due to its suitability for harsh radiation. If you look in the top right, that's a picture of the VPT DC-DC converter. And then for our second material, we had a MOSFET, which is a high-speed power switching device. And it has minimal energy loss due to its low resistance and also provides differential power to electrodes to help create a non-uniform electric field. That is also shown on the right, the second one from the top. Then for our step-down converter, we chose a Texas Instruments product because they're a very reliable manufacturer, and that the step-down converter is also very reliable under radiation. It also has a highly efficient voltage conversion, which helps to minimize power loss. And then for our logic circuit, that's also a Texas Instruments product. Just like I said, it's very reliable. That's why we chose that. It's a dual 4-input multiplexer to help manage data within the system. And it has the capability to perform logic operations that underlie the system's functionality. And that is shown in the bottom right corner on in the picture. And for our external structure, we chose an alloy of steel because its yield strength is 205 KSI, which is actually the highest of the 13.8 steels. And that is to help handle the vibrations from the Raptor engines. The material is also made up of similar to that of the landing gear, which allows it to be welded on. And as you can see, the cost of each material are listed below.
Our design will use electron beam welding, or EBW, as its main attachment method. Compared to fasteners and adhesive bonding, this provides the most reliable and least hazardous attachment method. Fasteners tend to add a significant amount of weight and complexity to integrate into our design, and adhesive bonding tends to outcast volatile products due to the continuous radiation exposure and just through general fatigue. Additionally, EBW was chosen amongst the other welding methods mainly due to the time efficiency, while still producing a high quality, low porosity weld that's free of contamination.
regarding the failure analysis for the electron beam well, we found that the failure location would likely be at the point or near the point of the well joint. And this would be its external attachment with the landing gear. So to test the failure analysis for this specific location, we had plans to conduct further reliability and environmental tests if we continued along with this design. But for now, we calculated the sample loads for the failure analysis regarding finite element analysis and abacus at the location of the weld to represent forces which would reflect Earth's standard gravity, the forces at launch, and the standard lunar surface gravity with a factor of safety of 1.5. And following this abacus experiment, we found that we would have end-to-end mission safety. We found that we would be able to comply with the initial set of requirements we drafted.
One of the big worries that we had for our project was the thermal analysis and the heat transfer exerted upon our project, the EDS. The biggest focus that we did for analysis was the electrodes. We assumed that all the components in the component box are able to do what they're manufactured for. They're well studied and they're well manufactured components that we again can assume that they can handle the electrical current that is going through it. Now, the electrodes, however, we are pumping, voltage into it, and the voltage, the wattage is calculated from the amps and the voltage that we have, and because we only have microamps and about megawatts, mega voltage, we really only have about 1 to 36 milliwatts. And if we divide that over the assumed area that is going to be applied on the electrode, we're only going to have about a heat flux of 458.37 watts per meter squared. So in the middle image at the top, we have our mesh for the electrode. And then at the top right, we have the kind of the boundary conditions for our electrode. So we assume that the outside of our little, if we assume it's say it's a cylinder, the outside is going to be about a temperature of 22 degrees Celsius. And why we assume that is because we are placing our EDS on the inside of the landing gear. So it's away from any lunar regolith. So that won't be compromised. And the astronauts are also inside the spaceship. So we're going to assume ambient temperatures for just the general inside of the HLS. And then we have the heat flux being applied on the top is marked in A, and the temperature is B. And then the bottom left, we have the temperature across the surface. And if you look closely at the top left of that image, we really only have less than 0.1 of a degree Celsius change, which is really low, and that's very good. It shows that our EDS is capable of handling the voltage that we are putting into it, showcasing that we are able to do what we want it to do. And then the heat flux, as shown on the bottom right, also very, very small. It's a very minor amount of heat, like voltage that's going through it, or wattage. So our heat flux is not big by any means, yet it's capable of removing the dust off the landing gears. So again, this is a big part that we had, and it showcases that our EDS is capable of handling the situation that we're putting it in. And yeah, we are GSI, and that's our EDS system.
Yes. You think you can hold on to the slideshow?
Yeah.
Then Ms. Thompson can have question first.
Oh, sure.
You can ask at home if he has any questions.
Oh yeah. Do you have any questions?
Maybe you can ask first. Do you want to ask?
Yeah, in terms of like the material costs, just on that slide, was that for each of the individual units? Or is that for? So.
Yeah,
each
so that's for each
ones?
individual one. It's not
Okay.
for all of it altogether. It's for each piece every time.
So the question was, is the cost for each individual unit? And JT responded saying, yes, it's for each individual one. It's not in total.
The thermal.
Hmm?
The question in the chat. Can you see the chat?
Yeah, I'm trying to get it back.
Because the first question is for the thermal analysis, what's FDA necessary?
The FEM.
The thermal analysis from Tom.
Oh, FEM. Okay.
You can see the chat from
Yeah,
here.
no, I just got it pulled up. We believe so. Yeah, we wanted to make sure that we were capable of we wanted to look at all aspects that's being used on the on our project, and we just wanted to make sure it was capable. So the other question is, your thermal analysis was for the little devices bonded to the legs. Why would those be at room temperature? Okay, yes, those were bonded to the legs. Our EDS is, we have I believe if you can see me right here. Actually, here, let me try and let me share the screen once more. And I can go back to the slide showing our. Okay, I just want to make sure you can see. All right, can you see our landing leg? Okay, so yeah, I hope you can also see my cursor. So yep, here's our landing leg that we don't have the exact dimensions or made like the model of the landing leg, so we made one of our own, just kind of showcasing it. Thank you over there. And here's our EDS on it. I just placed 4 on it. We as of right now, we don't know exactly how many it's needed, because first off, we don't know the exact dimensions of the landing gear, so we don't know, even if we knew how much square area EDS can cover, we don't know the exact dimensions of the landing gear, so we can't give an exact number of how many EDS systems will be required for each leg. And then why would those be at room temperature? Again, I'm assuming that they're at room temperature because they're on the inside, and because our astronauts are also inside, they're going to want to have ambient temperatures. And so if they want ambient temperatures, the rest of the rocket's going to have to be at ambient temperature.
So the question, what he mean was why you didn't use hand calculation instead of FEM? It's not a.
Oh, why did we use FEM instead of hand calculation? Okay, the reason why we use FEM instead of hand calculation is so we can get the temperature gradient across it. I mean, I could have done hand calculation to get the edge, but I wanted to get a good representation of the electrode, the temperature gradient across the electrode. In addition to heat flux. The landing legs are not inside, but so right on the slide shown, we have it on this side of the landing gear. I'm going to consider it the inside of the landing leg, because this is going to be hugging against the spacecraft right here, or mounted on. The rest of this, we're assuming it moves around and rotates, but this is going to be on the inside. And the reason that we have the EDS on the inside, like I said previously, is because we don't want it to be exposed to the elements or any dust that could compromise its functionality. And then you said, I think for something this simple, hand okay. I believe I answered your questions. But yeah, no, again, no hand calculations. I wanted to do an FEM. So I apologize. Any other questions?
Do you know how many are actually going to be necessary for each leg? Do you know how much area is covered?
No, we don't. So again, we don't know the exact dimensions of the landing legs. So because we also don't know the exact areas how much the EDS can really cover. But like matching that with how we don't know the landing leg dimensions exactly, we can't give an exact number at the moment.
And additionally, like just the surface area of the electrode is going to be what's repelling dust. And so for our design, it's meant to be more flexible where we can place it in different places. And also just to be flexible as in like we can change the area of the electrodes and also how many that we have. And due to that factor, it can be more flexible and we can apply to different situations.
Sure.
There's a question in the chat.
Yeah. So I suspect that you'd find the landing legs are not at room temperature. No, I agree. The landing legs would not be at room temperature. That I'm just saying that the inside, so the EDS is going to be inside of the spaceship. It's going to be connected to the landing leg, but the landing leg is going to be, so like the landing leg is going to be hugged against a rocket. And the inside of the landing leg is going to be inside the spaceship. So I'm just making the assumption that since it's not exposed to the elements or exposed to the vacuum of space, it's going to have the same temperature that's going to be inside the rocket, which is going to be my assumption of about ambient temperatures, which is about 22 degrees Celsius. What is the welding? What?
There, just take the welding question.
What is, yeah. Here, repeat it.
You say, what is the welding going to do to the landing legs? Are you talking about, are you referencing that there might be some kind of damaging effects to the landing legs? Are you saying that, I'm a little confused. Could you clarify that question? Was that your question, Tom? Yeah, at this point, we haven't really conducted extensive testing or kind of like research into the idea of how this is going to change the microstructure of the actual landing leg material. Just because we really didn't have access to that information at this time or the resources to perform that. However, the way we would go about understanding that would be through environmental testing as well as testing of the material following the welding. So that would kind of be our path forward from here. And then creating crack, would expect bonding would be preferable and lower risk. Yeah, that's definitely a possibility. Yeah, I think we would need to kind of conduct testing to verify that, but yeah, the comment was that it could potentially create crack initiators for everyone else. Yeah, this question regards, it's more of a comment. It's talking about how Tom doesn't expect that the crew cabin temperature would still be the same temperature on the outside of the landing leg. I think with our analysis of that, we really wanted to focus on mitigating the abundance of heat as opposed to the lack of it, just regarding our electronic device. But yeah, I suspect you're correct on that.
Here, repeat his comments so we all hear.
Yeah. Next question was, okay, conceptual question. Why do you think the approach will actually work? How effective will it be?
Embry-Riddle has done some research and design into this, and there's a video online that kind of showcases its effects and how effective it is. Where they just have two electrodes hooked up to about, I don't know, 12 inches by or 6 inches by 4 inches of like a little piece of glass, and there's like they put some dust on it and they activate these electrodes and it takes it off pretty effectively and quickly. So we're expecting this to we expect it to work theoretically. And how effective will it be? According to what we've seen and read, it should be a big part of a lot of the dust on it.
And adding on to that, we think that as a whole, there's definitely proof of concept here, with both the Embry-Riddle study, as well as some other kind of technical research papers that looked into this as a concept. But looking forward, we would need to conduct a number of tests regarding reliability and the ability of how we could refine this model to actually perform. But we think as a concept, this definitely is viable. Let's see if there's any other questions.
How is better do you need it to be always tested?
Yeah, I think with this, there's probably a number that's already established for the mission failure rate, which is probably similar to previous NASA missions. So I think it's general failure of 1/69 was the number that NASA continually cites in their systems reliability performance stuff. So I think the way we go about conducting this would be establishing requirements for the effectiveness of it. The second question was, how will you test it? I think there would need to be a large number of environmental tests, reliability tests, tests and ranging temperatures, kind of establishing a max and minimum temperature we'd expect. I think fully understanding and having access to all of the material regarding the material properties of the metal selected for the landing gear would be really useful for developing these tests. But yeah, a ton of different testing involving reliability, environmental, strength. As you mentioned, kind of how that weld would actually affect the microstructure and potential crack initiators. So I think by generating an FMEA, we could develop into that. Yes, that is the space. Oh, yeah, you're right. That was the space shuttle failure rate. Yeah, that was just a number off the top of the head. But yeah, I think kind of my general concept I was addressing there was kind of having an initial number and then developing reliability standards based on that. So I think working backwards is really the concept I was trying to express with that 1/69. All right, is there any other questions?
Yeah, I was just thinking, with the idea of like being able to change like the EDS's like surface area in order to mitigate things, why not just like completely cover a whole section of like either the landing gear or sections of the ship itself? Why not just do that instead of just having all these individual items, you know what I mean?
For us, I think it's just mainly about cost and weight effectiveness as well. We wanted to target crucial areas and also just to mitigate dust in areas that are most needed. And so with further testing, we can also research and see what areas are most prone to, I guess, jamming, corrosiveness, and also just damages caused by lunar regolith. And we can also apply that towards those specific regions. And so for us, like weight and cost effectiveness is also one of the things that we want to take into account. And that was our main reason why we only have that specific number. However, that can change due to just different requirements that are.
In addition to that, as Tom was saying, we wanted to make sure that we were targeting the most exposed areas. And what's unique about the targeted HLS is that the entire body is pretty much enclosed except for the landing gear. So that's why the EDS incorporated only using, that's why we incorporated the landing gear as it only comes out during ascent, the final ascent or the initial ascent and final descent on the lunar surface. So that's all I'm saying, by protecting the instrumentation inside where most of the regolith could be attached to and disrupting the main function of the rocket as a whole, we thought that would be more crucial placing it there opposed to placing it on the external.
Also for redundancy purposes.
Sure.
Just general redundancy is always good. So I think that was kind of how this design was initiated. So kind of we just had one initial point of contact. I think that's one point that we could see critical failure, but by establishing multiple kind of connections to the landing gear, we at least know we have some redundancy there.
Yeah, and like we said, we basically just assume the structure of the landing leg pictures, and also for me, I designed the landing leg also off of the Falcon X or 9, I believe. But I just based it off that concept to be able to like enclose the bottom of the HLS. And so for me, I see the critical areas which are like around the hydraulic system and also at the base of it. And so that's where we placed, I mean, the two EDS systems.
Do you guys think this would have any influences on other electronics, such as like landing sensors and anything like that? With this, do you think there would be any challenges necessary to design them around these electronics?
Are you referencing like power losses or?
No, more like just if there's any possibility that it influences just sensors necessary for landing needs.
Like interference?
Yeah, like any sort of like electromagnetic interference between.
I wouldn't think that would be an issue because they've already used it on stuff like cameras and radiators.
Okay.
So
Curious.
So I guess Tom is done with his questions, so then let me go back to the first page. So the first problem of your presentation is where is the page number? I mean, if people want to put some comment, it's much better if you have page number so we can. Okay, second one, next one. Okay, next one. Yeah. So the thing I'm feeling that the big logic of the whole presentation, and I think your actual the presentation start from like a rocket engine, but I am expecting to see something like a roadmap course, a big structure show at the very beginning instead of showing all the scattered information. I don't see the big logic of all the slides here. You know, you have every slide, you have a detailed information, but all these detailed information they are scattered. I need to see a big structure so I can know like what is the big picture of your design. So that is the one thing that is missing here. So I just feel like it's a little weird, like your presentation start from the rocket engine, and then the next slide is actually talking about the dust damage. So the order of the slides and the big logic is kind of missing here. And also in terms of the presentation itself, I think most of you did very well. The one thing I think I emphasized in the class is that do not read anything. Do not read anything because you always need to consider presentation is a communicating with the audience. And once you start reading, it just lost the audience cannot focus. So I feel like when you answer questions, it's like perfectly fine, right? I'm sure you can just talk without reading anything. You can do the present very well. You just need to be more confident. And we don't need your presentation to be like perfect. I mean, when you talk, you get stuck somewhere, it's fine. But we do not prefer reading anything, especially if you go to grad school, you go to conference, your presentation, or if you go to industry, if you do presentation in the company, never read anything.
Yes, yeah, I understand. For me, it's just more like a safe thing. Like
it just needs more confidence. If you're more confident, you absolutely know how to do the presentation. You don't need to read anything.
Yeah, I mean, I'm confident in my speaking abilities, and I do apologize.
It's okay. It's okay. Yeah. So
in a strange way, it's almost like less is more for presentations such as that. It just depends.
It's like when you talk to someone, it does not need to be exact word or exact sentence. It does not perfect. It just consider you are talking to a friend. Like when you answer his question, it's perfect. And also in terms of presentation itself, attention concept 1, yeah, this is the thing I also emphasizing in period in terms of presentation, the text here is just too tiny and too much. It's just distraction because if I want to read the content, it's hard for me to focus on your talk. But the presentation, the main purpose is talk. If I want to read, I read your report, right? And also the handwriting on the picture is cute. It just also, I mean, put in a more formal way. I don't think it's very professional you put some handwriting on the picture.
I think it's because those are older concepts that they never elaborated on later on, so it's just
okay.
pictures.
Yeah, these were the
that was submitted. But yeah.
And I think it's the same thing for the concept 2 and the concept
We just had a comment from Tom. I'll pull it up again. Do you want me to read that out?
Yeah.
Okay. Tom said, Agreed with Ting on the general presentation notes. First thing should be tell us what you designed, what it's going to do, and why it's necessary, then go into the details. I'd like to see less of the stuff you considered and didn't select, especially if you don't actually get into details of why you didn't select it.
So let's move on. Can you change the slide
Yeah.
to concept 2, concept 3? I think it's a similar thing. Yeah, and also the picture. I think the concept 3, the picture there is like it's hard for me to understand what do you want to show there. And the final design page. Yeah, so this one, I mean, you have dimension 45.6, 63.6. I understand. What's the point of put 6.858 millimeter? Why you need to have like 858, the significant digit here?
Yeah, I can see the logic there. I agree.
Right?
Engineers are really ruthless about significant figures. You don't really need to go that extreme.
What's the point to have like 858?
Couldn't tell you.
Yeah, and also the information here is just like too much. I mean, in a 30-minute presentation, do we really need this much detailed information? This is also emphasized in the presentation. Like, you really need to think about what you can put in the 30-minute presentation. It's not every detail of your design. And power requirements. So again, big picture of the whole presentation, big picture of power requirements. For this part, I mean, I just use this one example. I don't see the structure of this topic. I mean, power requirement is like the power part. Okay, I think this is the only slide in your presentation talking about power. I mean, if you think about the big picture of power, it's like, how much power do we need? What are the things that need power, and what is the total requirement? And what is our solution? And I mean, if we have battery, we have the solar array. What is our analysis? And let's say if you have solar array, what is the size and what type? And then final analysis, if our design satisfy the power requirement. That is a big picture of this topic. I don't see the picture here. I only see the scattered information.
Yeah.
No, I see what you're saying.
Yeah.
I think one thing I would say to that is like, with this general project, we don't have access to a lot of the material to give you that kind of final conclusion.
Yeah, but we want to know, like, each topic, I want to see a structure.
Yeah.
I'd
Yeah.
like to step in, and I think possibly when this was set up, there was a bit of maybe an error conveying the information, because this also is like a circuitry kind of diagram. And so I think like you make a very good point, especially when it comes to like the title of this slide. It could have been kept a little more relevant to the electric diagram and the power flow through that. But I see why that title might have meant that there's a little bit that seems to be left out.
Yeah. Can you read the message from Tom?
Yeah. Structurally, this is small and lightweight. The strength of the housing really isn't important here. The real structures consideration here is the vibration environment for the electronics.
I think that is the structure part.
Okay.
So,
Yeah, here, I'll
and
go to the
also
structure
for the
slide.
power requirement, I want to say that, be more confident in the presentation.
Oh, yeah, I know, I need to.
Yeah, I think your presentation probably just like you need more confident when you talk.
Yeah.
So,
no, I definitely.
yeah, this is not just for the presentation for this class. I mean, you guys we do a lot of presentation when you like as a graduate, and I feel like, as I said in the class, you guys are the only expert of your design, and you should be confident about your design. And you don't need to worry about it. I mean, we are only like more than 10 people here, but if you like do a presentation in front of a lot of people in a conference or anything, you definitely be more confident.
Yeah.
And also especially because I was like working as a mentor for the women students in the engineering. So it's more like especially for women students, we need to be more confident because we need to be proud of ourselves. It's like we are in engineering, we are in aerospace, right? And it's like those of the yeah. So just be more confident. That's what I mean. Be proud of yourself. Yes. Yes. So that's for presentation part. The failure analysis, the structure, I think this is the only page of your structure part. So as Tom said, well, the structure part is not a big deal here because it's small. Anyway, I agree. But if you really want to do structure analysis, I want to see some actual structure analysis. Instead of just saying here, okay, we did a structure analysis and we did FEA. I mean, I think I talked about in the structure analysis lecture, always hand calculation first. FEA is optional. If you don't hand calculation, don't even consider doing FEA. But I don't see in your report, I don't see any actual hand calculation. I mean, we have 1 week work on the structure. We have one separate report on just for the structure analysis, but I didn't really see any actual structure analysis in your report. And I see, it's the only value I see here is like 1.5 safety factor. I mean, where is the actual analysis?
Yeah, I think for this we tried to focus on more of like a high level view. But yeah, I understand how you'd want to see that.
We need to see the real work.
Okay.
Yeah. It's not like high. The material selection page. I think this is like a mix of the electronics and the actual structure material. So probably separate this. And also it's like too much detail information, like 2 busy slides on this one slide. Because normally when we say the material selection is really actually material selection in the structure part is structure material. And most of the things here, they are like electronics. So separate them. I think that's all the question I have. Yeah. Do you have any more questions?
Think about it. That was a cute dog. I guess just a few other comments myself. Just keep in mind, like a lot of engineers who are in part of a presentation are not necessarily. This is something I had to learn pretty quick when it came to like my lab presentations, which is that like lab directors, professors, other engineers, and who actually are like working in industry, they'll be pretty ruthless, but that doesn't necessarily mean they have any sort of antagonism towards you, and it's not a personal thing. They're just there to ask questions and see what you guys are all about and making sure that all your information is correct. I've felt almost like I was being harassed by my PI, but it's not like that. It's not that deep. So I guess just keep that in mind. And what else was I thinking? Oh yeah, and I definitely recommend don't stick to a like a PowerPoint like theme. I always find PowerPoint themes are terrible. Like that's not on you guys. This is just like the fact that like a lot of fonts and stuff just don't pop through, and it's kind of hard to understand. There's another thing I had in mind, but I'm trying to remember. But yeah, in general, I like your guys' design. I like the idea of it all. I'm really yeah, you guys did a good job. That's about it for me.
I'm sorry, I wanted to add onto your comments about the material selection.
Yeah.
Our design was just mainly circuitry components because it's just like a little electro in the dust shield. So I feel like it would make more sense to just put it all on one
Yes,
slide.
I mean, things this material selection is more of, if in the structure chapter, it's more of this structure material.
Yes, ma'am, but we don't like particularly have a
call it like component selection instead. Is that what?
Yeah.
Oh,
In
okay.
electronics, in section is in electronics section. Material section, when we say material section in the structure chapter, it's really structure material section. You can do some trade studies, you can do some analysis. Instead of just showing the result, this is the material we select. But actually what you could do is like we have a trade study, like these are the several candidates and why considering different like the density, the strength, fracture toughness, something, and this is a trade study and also the cost. This is why we select this material. That can be a single slide. That content itself can be single slide. And the electronic materials, it can be in the electronics, right? A different chapter.
So you're saying the alloy steel that we're using for the external structure should have been like a slide all by itself?
Yes,
All the-
yes,
okay.
yes, yes. Yes.
I had another thing. When it comes to yeah, just slipped my mind. Oh god. And when it comes to like answering questions as well, and this is a really major thing that I cannot stress this enough, don't give the person you're presenting any more than what they need, or else they're going to ask more questions. You want to almost leave them in a bit of a not suspense, I shouldn't call it that, but more of like not necessarily ambiguous either. You just don't want to talk too much is what I'm trying to say, but also don't like leave them with their question unanswered. That's kind of the tough part. It's tough to say lol. But yeah, it's a thing that I had to learn pretty quick too, is like and I've been berated about it before too. It's just like you don't want to be like, when you're answering questions like, yeah, we're using this material, but we can also, don't do an aside while you're answering a question. Like, don't question yourself in the middle of answering a question. It just kind of comes off as giving a little bit more confidence in that respect. That's a pretty important part. And what was the other thing? Oh, and don't ever be afraid, especially during like presentations when it comes to people who are like in industry or anything like that. Well, industry can be a little bit more rough because people are like, spending money. There's money being had. When it comes to like presentations in terms of like research and everything, don't be afraid to say, I don't know. Or like, we'll look into that. I should look into that. Like, don't be afraid to do that. That's not necessarily a problem, unless you're saying I don't know the whole time. Like, then that's probably a problem. But it's just like, it just comes down to like, if it's something that's like really nitty gritty, like I remember a particular presentation I gave where I used a function which I didn't actually use in my code, but instead I actually made what was it? It was like an integration that was non-dimensionalized, and I didn't change it from that, and I've been berated about that, and I started thinking about it, and like I said, I don't know about the whole time my lab director was asking about it. And he had to essentially stop the presentation because I couldn't do it. I wasn't correctly expressing how I was actually doing it. So it was pretty embarrassing, but like, it just kind of comes to the fact that it's like, to some extent you should know what you're talking about, but you also shouldn't like assume too much of what you're doing, if that makes sense. I'm trying to express this the best way I can, but yeah, it's pretty much it. What does Tom say? Yeah, exactly. Yeah, that's just my 2 cents.
Tom, do you have any more questions? Okay, thank you so much. Thank you,
Thank you,
guys.
Tom. Thank you.
Thank you, Tom.
Congratulations.
Good job, guys.
What happened to the report? Final report.
I'll have a I'm writing a paper right now, but